Welcome to Chapter 8. So we are coming off of what was the longest of our chapters. This one should be the shortest for sure. This is Advanced Theories in Covalent Bonding. All right, and so again, right, we've learned a little bit about our covalent bonding in the past, and so we're going to touch a little bit more on that, but we're not going to go super in depth because again, this is not like one of those topics that, is like one of the most important of all of our chemistry, but it is something that we kind of need to get down. So our valence bond theory is going to help us understand a little bit more about why we get the shapes that we do, because of the overlap, right, and the fact that we want to share those electrons, right, when we've got our bonds. When we've got a covalent bond, right, it's easy to explain some of the different types of bonds, but sometimes it doesn't work out as smoothly as we think that it should. So in general, when we talk about our valence bond theory, our number of bonds is based upon the number of unpaired electrons that we have. Okay, so if we think about that, right, then we might be able to think about, okay, if you've got something like a fluorine, right, and so you've got your fluorine there, and your fluorine has that one unpaired electron. And so when you've got that one unpaired electron, and I'm going to end up covering this up here in a minute, but it's got that one unpaired electron. Okay, fluorines, they really like to have like one bond. Okay, and that's really easy for us to explain because you got that one lone electron by itself, and it can then overlap with another species and form a bond. And hydrogen in the same way. So let's look at those two. I believe that they're going to pop up here, hopefully. Yep, okay, there's hydrogen. Right, I've got one hydrogen. It's got a lone electron, right? It's a non-paired up electron. I got another hydrogen with that, and so they can then pair up together and form an overall bond, that H2 molecule. Same thing there with our fluorine, right? Each fluorine can come together there, and they've got one unpaired electron. They form a single bond. Okay, and that works out really well when we've got these diatomic molecules. Okay, but that explains that, and it also explains why our noble gases don't bond. Right? If you think about like a noble gas, say like our neon, right? Neon is saying that it has no unpaired electrons, and so when you've got no unpaired electrons, you've got nobody to be able to bond with, and so it's really happy to not bond. Okay, but this doesn't explain everything else. Okay, so if we were to start thinking a little bit further down, right, what's happening with some of our other things that are out there? So again, let's go and we're going to look at some diatomic molecules. All right, so again, hydrogen has one unpaired electron, and chlorine has one unpaired electron, and they form a single bond. All right, and I want to point out that when we have single bonds, we're going to call those sigma bonds. All right, each oxygen here has two unpaired electrons. All right, and these can each form a bond. And when we have two bonds, we've got a double bond. One of them is a sigma bond, and one of them is going to be called a pi bond. Right? And I do want to point out then that when we had our nitrogens, they like to form triple bonds. All right, and a triple bond, and we're going to describe what the difference is between a sigma and a pi bond is soon enough, but a triple bond is one sigma bond and two pi bonds. Okay, so we're going to end up at the very end of this chapter by counting those types of bonds. So keep that in mind of like that when you got a double bond, it's a sigma and a pi. Single bond is just a sigma, and a triple bond is a sigma and two pi bonds. All right, and so these number of unpaired electrons can be determined from like their electron configurations. So if we looked at like oxygen, Right? It's 1s2, 2s2, and then 2p4. Right? And so it would have in the 1s orbital there 2 electrons, and the 2s orbital 2 electrons, and in the 2p orbital, remember there are 3 2p orbitals. We like to fill in 1 electron at a time before they start to pair up. So 1, 2, 3, 4. Right, there's 2 unpaired electrons. And so oxygens like to form 2 bonds. Right, and so these are really easy for us to explain. We've got just these diatomic molecules. They work out really nicely. All right, now that being said, right, it doesn't work for everything else. And so then we're going to have to explain how bonding occurs. And we're going to do that by something that we're going to call hybrid atomic orbitals. All right, hybrid atomic orbitals, right, is what happens when we have small molecules, right, but we start to have bonding that we cannot predict from the valence bond theory that we had before. Okay, and so what's going to happen here is that other bonding is going to come from what we call the hybridization of our orbitals, which is just when orbitals actually mix together. Okay, so our orbitals aren't just these like things that are individual out in space, right? They actually are sitting there where they overlap with each other. Because if you think about the nucleus of something, right, and then around that nucleus you might have a 1s orbital. Right? And that's, remember, a sphere. And then you've got a 2s orbital, which is just a little bit bigger, but it's just a 3-dimensional space, but it takes up some of the exact same space there. And then you've got those 2p orbitals, right? And they are there, and they're in 3-dimensional space, but they're also kind of like, they could intermingle with each other. Okay, and so let's look at, first, I've got beryllium chloride here as an example. All right, and it says that beryllium chloride has no lone electrons, because if we look at the beryllium itself, it has the electron configuration of 1s2, 2s2. And so if we think about that, right, we have 1s, and then we got a 2s. All the electrons are paired up, and yet beryllium chloride actually forms 2 bonds. The beryllium forms 2 bonds to form this linear molecule here. All right, and so then how can that possibly occur? Okay, well, what happens here is that we're going to get a mixing of some orbitals. And so what I mean by that is that not only do we have those 2s orbitals there, but we also have some 2p orbitals that are there. The second that you open up a new principal quantum number, all of the orbitals are actually present. Okay, and this is part of the reason why we get expanded octets, is because when you reach that, like, say, group 3, or sorry, not group 3, period 3, okay, then you've got those 3s orbitals, you've got 3p orbitals. Well, you actually have these open 3d orbitals where other electrons can go in. Once you reach this 2s, there's actually those 2p orbitals that are there, but they're just empty. All right, and if they're sitting there empty, what can happen is that they can actually mix with the s orbital. And so if that s orbital mixes with one of the p orbitals, right, if it mixes with one of the p orbitals, then it can form, all right, so notice that there's one of them is an 2s orbital, one of them is a 2p orbital. So there's 2 orbitals that are mixed together. It's going to form 2 sp orbitals. All right, and then we also still have 2 unused 2p orbitals up there. They didn't do any of this mixing yet. All right, and so we've got these 2 sp orbitals that are sitting there. They're mixed together, And now those electrons can go into those, and now they are not paired up. And so now we've got unpaired electrons, and those are allowed to then bond. All right, and so we get then bonding to occur then. All right, and so this is called sp hybridization. All right, and we're going to be able to figure out how it's really not that difficult for us pretty soon to be able to figure out what the hybridization is of something. All right, and that's going to be by counting regions of electron density like we've done before. It's going to be super easy. We're just going to add something to kind of our tables. All right, next up, let's move on to what if we mixed an s orbital with two different p orbitals? Okay, when we do that, we call it sp2 hybridization. Okay, and when we mix with sp2 hybridization, if I mix with an s orbital right, if I mix an s orbital, that's not right, okay, and I mix two of the p orbitals, should freeze on me right now. That's not good. Okay, if I mix the s orbital with two of the p orbitals there, it froze on me. I hope that it came back okay. With two of those p orbitals, right, then I got an s and two of the p's mixed together. I've got three orbitals total, so I have three sp2 orbitals. Right? Notice that I now have the ability to form three different bonds. Okay, and this is something like BF3. All right, so boron, right, again, has the electron configuration. So boron is in group 13, and it has the electron configuration of 1s2, 2s2, 2p1. Right, you would expect that it would form one bond because it only would have 1s2, 2s2, 2p1. It has one unpaired electron, and yet it forms three, right? And that's because of these three hybrid orbitals there. And so we actually get this to form this trigonal planar shape, like so. All right, sp3 hybridization. Okay, this is where we are going to, right, mix an s orbital with all three of those p orbitals. All right, and so all four of those have come together to form four orbitals that are called sp3 hybridization. sp3 hybridization has four total ones. And so this explains something like our methane. Right, methane there. Again, right, carbon is 1s2, 2s2, 2p2. It really should only form two bonds. And yet, carbons love to form four bonds. Okay, and that's because of this hybridization. All right, we can also have other hybrid orbitals. We can start to mix with d orbitals as well. And it's hard to see there, but we can get sp3, and if we mix then with a d orbital, right, that is sp3d, again, it's kind of small, so I'm writing it out there, and then we could actually mix with two d orbitals, sp3d2, That's where we get like the octahedral shapes and stuff like that, right? And triglypyramidal comes in there. All right, so this is going to help us also explain multiple bonds. Right, so again, right, single bonds are always formed by a direct overlap of two orbitals. So we saw that earlier with our hydrogens. Oh, terrible. Oh, I'm doing a terrible job drawing it. Okay. There we go. Right, our hydrogens, like there's a direct overlap of those s orbitals. There's not really very good spheres, but you get the idea there. Or we saw our fluorines with those p orbitals directly overlapping. When there's a direct overlap, we call those sigma bonds. Okay, when there's not a direct overlap, but when there's more of like kind of a side-to-side thing going on there, right? When there's a side-to-side overlap, we're going to call those pi bonds. All right, and so again, remember down here, right? If you got a single bond, you got a sigma bond. If you got a double bond, you got one sigma and one pi. That ends up to be 2. Triple bond is a sigma, and 2 pi bonds, that equals 3. Okay, so, right, like a double bond is from something here like our CH2 or sp2 overlaps. Okay, so what I mean by an sp2 overlap, right, is our sp2 kind of has these shapes here. Okay, and so what we've done is we have used up an s plus a couple of p orbitals, right? That gives us our sp2, but there's an unused p orbital, right? There's an unused p orbital in both of these carbons. And those unused p orbitals can have this side-by-side overlap where another bond can occur. So first off, right, there is the direct overlap here. That's our sigma bond. And then we've got this side-by-side overlap there. That's our second bond. That's our pi bond. Okay, now if you've got in sp hybridization, okay, so sp hybridization, right, usually leads to like a linear shape because you're mixing an s and a p and you kind of get this linear shape associated with it, right? Which is what we saw from that beryllium, or that, yeah, beryllium chloride before. And so this is your sp, and so you get a bond out here and a bond out here, right? Remember that sp is like kind of like two different orbitals that can have two different bonds. Both of those are sigma bonds, all right? But we've mixed an s and a p, which has left us with two unused p orbitals, and those unused p orbitals can now form bonding, and those are side-by-side bonding, and those are pi bonds. And again, they're kind of hard to see, so they're kind of pictured here, but there's some side-by-side bonding there, and in the blue there's some side-by-side bonding. Each one of those, right, one of them is the second bond, one of them is the third bond in our triple bond. Both of them are called pi bond. All right, now, can we count sigma and pi bonds? All right, so these should sum to the total number of bonds right? So the total number of lines. Okay, so sigmas, every type of bond is a sigma bond. Okay, so I'm going to do sigma in red, and I'm going to do pi in blue. Okay, so sigma is 1, 2, 3, 4, 5, 6, 7, 8, 9. And then pi is 1 and 2. Two pi bonds there. Okay, now, right, a little bit tougher is where we've got these like little stick figures here, like the cyclopropane and the cyclohexane. There's actually hydrogens there. Oh, I don't want to do that in blue. That are coming off so we got to count them as well. So like our cyclopropane there has 1, 2, 3, 4, 5, 6, 7, 8, 9. And 0 pi's. All right, same thing here with our cyclohexane. Each one of those also has 2 hydrogens in there. All right, so again, it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then I'm going to count 13, 14, 15, 16, 17, 18. 18 sigmas and no pi bonds. All right, last one down there. Right, again, I don't have any with triple bonds in here, but if there's a triple bond, remember to count each one of those as 2 pi bonds. Here, why don't we just do, instead of doing the last one, by the way, right, is 12 sigmas and 3 pi's down there. Let's see. All right, let's do that one. Okay, so I've got, for my sigmas, I got 1, 2, 3, 4, 5, 6. And for my pi's, 1, 2 for the triple bonds, 2 pi bonds. All right, and so that's how we're going to count those. So those should be relatively easy. All right, now, last thing that I want to point out is, remember I said that when we were talking about our hybridization, okay, if you have 2 regions of electron density, the hybridization is sp. So again, if we're drawing them, we can figure these out. If we have 3 regions of electron density, it is sp2. So this again goes back to the previous chapter of doing Lewis dot structures. 4 REDs, it's sp3. 5 regions of electron density, sp3d. And 6 regions of electron density, sp3d2. So that just adds one new thing that we can talk about. Once you've drawn something, can you give me the electron geometry? Can you give me the shape? And now, can you tell me what the hybridization is of that? All right. Finally, another chapter down. We'll see you then for chapter 9. Gas laws.